Alright, so this is the second video of the night for me that I'm making for you guys on the Unit 2B, Unit 3 notes. I know that there's a lot of questions in those two units that we put into the notes, and didn't get to a lot of them in class or kind of rushed through them, so that's why I want to make sure that we definitely had a video of these units that you guys could look back on and hopefully process or remember them a little bit better. So in these notes, we're going to talk about even, odd, and neither functions, what that means, what they look like, even and odd degreed functions, what their end behavior looks like. We'll do a bit of modeling, constructing an open top box. Also do some curve sketching, so I'll actually sketch what a function looks like without even touching my calculator. We'll talk about where a function is increasing, decreasing, where it's positive, where it's negative, so some vocab to make sure we know, and how we can state their intervals. I'll also do some rational expression work, which I just mean fractions when I say that. So we'll be simplifying fractions, multiplying fractions, dividing fractions, adding. I'll do some complex fractions as well, which I use the box-in method for. We'll also be solving rational equations. Notice there's an equal sign in there. I'll briefly do some radical problems, although we have done those a lot more recently. And then I'm going to do all these rational word problems together. Particularly, I know you guys don't like the mixture problems. I don't like the mixture problems, but we're going to go through those and hopefully make those a little bit more easy for us to remember. Alright, so I just got to fast forward back to the first question. Alright, so starting right from the beginning of our 2B notes in here, let's just talk about what even, odd, and neither functions mean. I'm not saying even or odd degreed. I'm really talking about symmetry in this. So I'm actually going to start with the graphic representation. So when you have an even function, an example of an even function would be y equals x squared. So I'll just sketch a little function of this. This is even because it has symmetry with the y-axis. Okay? So y equals x squared would be 1, y equals x squared plus 2. Even if you like shifted it up 2 units, it still has symmetry with the y-axis. An odd function example would be y equals x cubed. So I sketched that the best I could in there, and that has symmetry with the origin. And what that means is that if you were to take this image and rotate it 180 degrees around, or take your paper and literally flip it upside down, the picture would look the same. Okay, so some people will say, oh, it's odd because the function goes through the origin. No, that's not it. It's not that it goes through the origin, it's that it's symmetric with the origin. Because technically, this is a function, which is called a hyperbola, that is not going through the origin, but is odd because it has symmetry with the origin. Okay, so you'll learn more about that next year in pre-calc. So, visually speaking then, our even functions would be just b. He's the only one that's even. He has symmetry with the y-axis. Odd would be c and e. Those have symmetry with the origin. The last two are neither. They don't fall into either category. Okay? Algebraically speaking, if you have an even function, what this says is when you evaluate it at a negative value, or negative x, you'll get f of x back. So if you evaluate it at negative x, you're going to get the same function back. Okay, so that's even. Odd says if you evaluate a function at negative x, you'll get the function back, but it looks like it's been multiplied by a negative 1. So you'll get the exact opposite thing back. And if you get neither of those, the function's neither. Alright, so going through this example I have bulleted here, if I evaluate it at negative x, a negative raised to an odd power will still be negative. And then this is -1 times a negative, which will make it go positive. So when you compare this to the original, the signs have changed to the exact opposite, which means it looks like this is equal to -1 times f of x. So therefore, this function's odd. Okay, the one below it's a little bit trickier. Okay, this would go positive, but still minus it. Now, I think we can all agree it's not even because I didn't get the same function back. However, the sign changed in the top. Okay, it doesn't have to change in the bottom. Okay, that would be like saying, all right, 3/4 times -1 is -3 over -4. Like, we know that's not true. Okay, so you would just write -3 over 4, right? So this looks like your function times -1. Right? If you multiplied that by -1, you would write -x over 1 minus x squared, and that's what you have. So therefore, this is odd. A lot of students think it's neither. All right, let's talk about end behavior now. End behavior is like those dancing guys. They're called, where like their arms are up, their arms are down, they're opposite, okay? I'm actually going to draw a little chart over here. So even, and then this will be when the leading coefficient's positive, and this will be when the leading coefficient's negative. All right, so even degreed, so x squared, x to the 4th, x to the 6th, and so forth. If you have a function that has an even degree, or is even degreed, and the leading coefficient's positive, its end behavior looks like this. If it's negative, it's the exact opposite. That's your whole happy versus sad parabola that you guys learned back in Algebra 1. When the function is odd degreed, like x cubed or x to the 5th, your end behavior will be opposite. If the leading coefficient's positive, I always remember that it will end positively, so as x approaches infinity. If it's negative, it will end negatively. Okay, so like if I look at this first example, I'm thinking to myself, it's odd, its leading coefficient's positive, therefore it's going to be opposite and end positively. Now, when I describe my end behavior, I use what's called limit notation. So I say, as x approaches negative infinity. That's a fancy way of saying you're looking to the left. As you're looking to the left, you would expect your function to be going down, which means f of x is approaching negative infinity. So as you look to the left, your function's going down. That's essentially what that's saying. As x approaches infinity, so as you look to the right, I'd expect my function to go up. So f of x is approaching infinity. Done. All right, modeling problems. An open box is to be constructed from a square piece of sheet metal by removing squares of size 6 inches from each corner and turning up the edges. If the box is to hold 294 cubic inches, what should the dimensions of the sheet metal be? All right, so I've got a square box. I'm cutting out corners with 6 by 6 as dimensions. I don't know the dimensions of the sheet, but I do know it's a square, so I'll call it x by x. Now, hopefully you remember the demo from class. I can't exactly do it in Screencast-O-Matic right now. But you're creating an open top box by folding up along these dashed lines. Okay, you could even try doing this yourself and see how it shows up or how it works out. When you create this box, this is your length and width. This would be your height. Okay, length, width, height, or vice versa in here. It doesn't matter. Okay, so when it's talking about 294 cubic inches, that's a volume. So we're going to set volume, which is length times width times height, equal to 294. Okay, my length, which would be this in here, would be x, but take away 6 and 6, which would be 12. Same thing here on my width, x minus 6 and 6 is 12. So I'll just write this as x minus 12 squared for length times width. the height is that corner you're cutting up along. So that's 6. Now, in order to go ahead and algebraically solve this, I would divide both sides by 6 and get 49. Take the square root like I did in my last video. Oopsies, I should move my plus or minus over here. So you get 2 solutions. X minus 12 is equal to plus or minus 7. So 19 and 5. But 5 doesn't make sense because you can't have a length of 5 and then take away 12. That doesn't make sense. You wouldn't even have a box. So 19 is your X value. So your sheet metal must be 19 by 19. And you could check this. If you did plug 19 in for X, subtracted 12, squared it, multiplied by 6, you should get 294. All right, question 3, we're going to have a parabola, y equals 36 minus x squared. And we're going to have a rectangle fit underneath that. Okay, keep in mind that this corner could drag in either direction, depending upon how short you want it to be or how tall you want it to be and so forth. The idea is that the rectangle is bound beneath the parabola and between these axes. Okay, I want to find the value of x, which would be this, like your length, such that you would create a box with the greatest area. Okay, now we all know area is equal to length times width. So think about this x as the length of your box, or width, either or. This height of the box, or width, whatever, length, width, whatever, is going to be some y value. It's parallel to that y-axis. So at this point, I know the area of this rectangle is equal to x times y. What's y though? Y is 36 minus x squared. Because that corner of the box, or corner of the rectangle, is always on the parabola. When I want to find the maximum x value, I'm going to plug this into my y equals in my calculator. So let's see, can I pull this up? Okay, so I've got x times 36 minus x squared. Okay, and when I graph a standard window, I really don't have anything exciting. I'm looking for a maximum point, which I clearly don't have in my window. If you look at your table of values, it'll give you an idea of where your function is. So at x equals 0, it's at 0. It shoots up into the 80s and then drastically hits back down again. So I'm going to extend my y's. Whoopsies. I'm going to set my y's to be like 100. Yeah, I know, my OneNote just crashed again. Ugh, hold on. All right, we're back. I probably just have to restart my computer or something. All right, so I plugged in my y max at 100. Graph. Check it out. That's what I wanted. In order to find that maximum point, I'll hit second trace. Option 4, which is a maximum. Left bound, you get to the left of it, please hit enter. A lot of students think that their calculator is like broken. No, you just have to hit enter. Right bound, I get to the right of it. Okay, I'm pinching in, see how the arrows are pinching in on an area? It's saying, hey, I'm gonna look for a maximum in this area. When it says guess, you can just hit enter again. And there you go. So our x value is 3.46. This 83.13 number, that's actually your area. That is the maximum area for if you were to go out on your x-axis, 3.46. All right, curve sketching. First, I'm going to algebraically locate the zeros here. So I notice there's a GCF I can pull out, so I'll do that first. This factors. Let's see, x minus 3, no, x plus 3, x minus 1. So my roots are 0, -3, and 1. But keep in mind that this has a x equals 0 happens twice. So you have a multiplicity of 2, which means you're going to see a kiss in the graph. All right, so let me go ahead over here and do this. I'm just going to plot these. So x equals 0, -3, and 1. Okay, now my y-intercept is pretty obvious here, but just in case it doesn't happen to go through x equals 0, the y-intercept is always equal to where x equals 0. So if you plugged 0 in for each of these x's, you'd see the entire thing would end up going to 0. So that's your y-intercept, which again, I know it makes sense here. Now, since this is an even degreed polynomial and the leading coefficient's positive, I know my end behavior is going to look like this, just like what we reviewed earlier in this video. So I can actually fill in the ends of this first. Okay, now at x equals -3, because the multiplicity is 1, I'm going to cross the x-axis. Okay, then I gotta come back up and hit the x-axis at 0. You're going to see a kiss in the graph though, which means we touch the x-axis, but then we go back in the other direction, and then we gotta come back. And there you have it. That's your function. Cross, kiss, cross. End behavior matches everything that I expected. All right, so I have a function to the right. If I had to guess, this is a third degree polynomial because I see 3 crosses, which are multiplicities that are odd. So I'll say 1. 1 plus 1 plus 1 is 3, so this is a cubic function. I want to know on what interval the function is increasing. Increasing just means from left to right where the function rises. So I'm highlighting that for you guys. Whenever you say intervals, it's just the x's I care about. I always say I only care about the x's. So from way out here, right, this is going to keep continuing. From -infinity up until this stopping point, we're increasing. That x value is -1.732. So that's my first interval in which I'm increasing. Okay, then I'm decreasing, and then I'm increasing again. So I start up again at 1.732, and I'm going to keep increasing forever, so I'll say until infinity. Done. Decreasing is what was going on in here. This was a decrease. Okay, so again, I only care about the x's, so from this starting point to this stopping point, I'm decreasing. So from -1.732 to +1.732, I am decreasing. When I ask you where the function is negative, I'm asking where it's below the x-axis. So I see 2 places, here and here. Now if I only care about the x's, from -infinity up until -3, the function is below the x-axis. So that's my first interval. Then I go from 0 to 3 again, where I'm below. So that's my second interval. And there you go. Done. Where the function's positive is where it's above the x-axis. So I see a location here. Oopsies. And a location here. Okay, so I only care about the x's, so from -3 to 0, I'm positive. From -3, continuing on forever, I'm positive, so that's my interval. Done. Okay, so make sure you know this vocab. Oh, and you don't state any y's in your coordinates. Those are the biggest mistakes we make. All right, so this is some Unit 3 review. First thing I'm going to do is just simplify question 3. You always have to factor and then cancel. And it's always one numerator with, I should write it like this, with one denominator. You never cancel like factors if they're both in the numerator, okay? The numerator, I'm going to guess I have to factor by group here because there's 4 terms. Bottom's dots. Okay, and I was right. Here's my common binomial, so I'll write this as x minus 5 times x squared plus 4. Okay, so at this point, I know that my numerator is x minus 5, x squared plus 4. My denominator is x plus 5, x minus 5. You guys are seeing a common factor that I can cancel, one in the numerator, one in the denominator. So my result is x squared plus 4 over x plus 5, and that's your simplified answer. Now, there is something called domain restrictions here. What that means is I need to look at this denominator and ask myself, what values of x can I not have? Because it would cause the denominator to go to 0, and that would mean that it's undefined, and I don't want that. Always look at the part where you factor the denominator. Okay, now I know I canceled out the x minus 5 when I was simplifying, but he still counts for where the original function goes undefined. So I still have 2 domain restrictions. X cannot be equal to -5 or +5 because when I set each of these equal to 0, that's what those would solve for. If you plug -5 in here, that would go to 0. If you plug 5 in here, that would go to 0. So those would be 2 values you can't have, so that's why they're called restrictions. Okay, and with multiplying and dividing, you're still going to factor, then you're going to cancel. Okay, and when you divide, it really is a multiplication problem, and we change it by using key chains flip. So we'll practice that at question 6. All right, question 5. Let's factor here. So I'm just going to go out of order here. I know this is dots. This just has a GCF of 2. And down here, I'm actually going to write this out twice just to make it really clear which factors I can cancel. Now this guy, if I had to guess, I would say he has 2x plus 1 as a factor. Rather than doing my triangle method, I'm just going to guess and check it and say 2x plus 1 is probably a factor there. Now if I want to get a -4, I would need that to be -4 or -4. So let's just see real quick. Does this make sense? 2x times x is obviously 2x squared. My outer term gives me a -8x. My inner term is a positive x, which sums to -7x. So yay, I factored it right. Okay, factoring's done. And notice how I was pretty strategic there. I didn't feel like doing the triangle method for this, so I used the problem to help me. I saw this down here and thought to myself, they probably want that to cancel with something in this top trinomial, so that's how I use the problem to my advantage, to factor a little faster. All right, start canceling stuff, right? Boom. What else we got? An x minus 4 and an x minus 4. All right, now I can cancel, I'll do this in another color. I can cancel x minus 4 with 4 minus x, but you can't just switch terms around with subtraction and say that they're equal. We know subtraction is not a commutative. But these do reduce. They just don't reduce to 1. They reduce to -1. So I'm going to throw a negative out in front, and I circle it so I don't forget it. So what I have left at this point is -1 times 4 plus x all over, looks like just 2. So you can leave it like this, or if you want to distribute that negative, this is -4 minus x all over 2. So if you do distribute, make sure this becomes a negative x, you don't leave it as a positive x. All right, and then division is just like multiplication. You just have to flip the second fraction. So change that to multiplication and then flip it. I'm going to factor as I go. This numerator is soap. Oopsies. Okay, and if you need to review SOAP, look at a previous video. Bottom stats. Okay, see how I flipped it? So now the x squared's in the bottom. In the numerator, this is x minus 5 times x plus 3. And I go ahead and cancel. These are opposite factors again, so you're going to get a negative 1. So my final answer is negative x minus 5 times, I don't know why I skipped over this, 9 plus 3x plus x squared all over x squared. And please do not cancel those x squareds. That would be slashing. You can only cancel across multiplication, so please leave those as is. All right, now this goes back to, middle school, elementary school. Anytime you add fractions like, say, 1/2 and 1/4, you needed a common denominator, right? So you do 2 over 4 plus 1/4 is 3/4, right? It's nothing new here, guys. It's the same idea, like same concept, but obviously now it's in terms of polynomials. So I need a common denominator. So first thing I'm going to do is factor this denominator. And I notice that it's very similar to the second fraction, yet it's missing an x plus 6, and this is a 6 minus x as opposed to an x minus 6. So I'm just going to take a step here and make my life a little bit easier. I'm going to write that second fraction as x minus 6 because that's going to make my life easier because then I get those two at least match. But if I do that switching, you're going to have to make this top 6 be the opposite sign. So it's now going to be negative. Okay. Now, just like what I modeled before with 1/2 plus 1/4, this guy needs an x plus 6. So I multiply the top and bottom by what it needs. That way it's like you're multiplying by 1, because x plus 6 over x plus 6 is 1. Distribute that negative 6. And I'll write that common denominator once, which is what you would do when you add fractions anyway. Combine like terms. Now don't stop. You got a GCF you can take out of 6, right? So this numerator factors to 6 times x minus 6. And hey, look at that. X minus 6's drop out. So your final answer is 6 over x plus 6. That was a fun one. All right, complex fractions. First thing you need to do is take any of these like floating terms and make them fractions. So I'll put them over 1. And between 3x, 4x, and 1, you're going to come up with a least common denominator or lowest common denominator. So your LCD between 3x, 4x, and 1 is just 12x. So I'm going to go through and multiply each of these pieces by 12x over 1. And I'm going to do what I call boxing in each of those terms. So it's like I'm creating 3 mini multiplication problems here. In my numerator, in this multiplication problem, my x's will drop out. And 12 divided by 3 is 4. So in my numerator, I have 4 times 4, which is 16. All over. In my denominator, this lower left, x and x drop out. 12 divided by 4 is 3. 3 times 6 is 18. Nothing cancels down here, but that's okay because my denominator is 1 to begin with. Now this actually does reduce further. Each of these is divisible by 2. So my final answer is 8 over 9 minus 12x. All right, last question on this page is solving rational equations, which means there's an equal sign in there. So do not confuse this with expressions. So this is a rational expression, not an equation, because it doesn't have an equal sign. When I solve rational equations, I still get a common denominator. But once I adjust my numerators, I can drop or ignore the denominator. Okay, and you'll see me model that in this problem. First of all, this denominator over here factors to x minus 6 times x minus 2. So it's very clear to me that this is actually going to be my common denominator between all three of these terms. Now, one thing off the bat that I'm going to keep in mind is I have two domain restrictions. X cannot equal 6 and it cannot equal 2 because that would cause these denominators to go to 0. So keep that in mind. So if you get those as a solution, we have to reject them. All right, here we go. So technically in this first term, I'm multiplying the top and bottom by x minus 2. Okay, so this numerator would be just x minus 2. Over here, this guy needs an x minus 6. And this guy has the common denominator, so he needs no manipulating. Once I've done all that manipulating with the numerator, I can ignore the denominator. So what I have is x minus 2 plus x times x minus 6, or x times x minus 6, yep, equals 4. And guys, at this point, you're just solving like you normally would. So I'm going to go ahead and do this. Okay, so those are my two solutions. Notice how I got x equals 6. Remember, I can't have that, so I have to reject. That's what's known as an extraneous solution. And so x equals -1 is my solution. All right. Whoa. All right, it is already a 32-minute video, and I'm just getting to the last set of questions. So here we go. Radical equations. We isolate the radical and square both sides. Squaring undoes square roots. Okay, I can add over the 7. So x equals 11. And let's see, does that make sense? Square root of 11 minus 7. 11 minus 7 is 4. Square root of 4 is 2. It checks. The biggest thing with these that you guys tend to forget is to check your solutions, particularly the ones that end up having two solutions. One of them usually rejects. I don't want to say all the time, but usually when it's a multiple choice question, one of them rejects, and that's how students get multiple choice questions wrong. So please make sure you always check your solutions in the original equation. All right, working together problems. Suppose Jeff can paint a fence in 6 hours. So Jeff can do one job in 6 hours. If Tim helps him paint the fence, they can do it in 4 hours. So together, they can paint the fence in 4 hours. How long would it take for Tim to paint it by himself? So one job in an unknown amount of time. So Jeff plus Tim equals together. So just like before with rational equations, we need a common denominator. So in this case, it would be 12x. Okay, in order to get a 12x, I would multiply 6 by 2x. This would need a 12, and this last part would need a 3x. Ignore the denominator. 2x plus 12 equals 3x. So yikes, it takes Tim 12 hours to paint the fence by himself. Not the fastest painter. All right, mixture problems. A 50-pound bag of dog food contains 40% rice. How many pounds of rice should be added to bring the mixture up to 60% rice? From what students have told me, they like to do this as a table, so that's how I'm going to do it. We've got our dog food, our rice, and our mixture we want. First column's amount. I'll call this percent rice, because that's really what I'm manipulating, what percent rice we're going to have. And the last columns are total. All right, so we have 50 pounds of dog food. That is 40% rice. How many pounds of rice, so this is unknown, needs to be added to bring the mixture up to 60%? Now I have a couple blanks to fill in. Rice is technically 100% rice, right? Like it's pure rice. So this would be 100%, so 1. If I had 50 pounds and I added X more, I would have X plus 50 as my grand total of pounds for my dog food. When I figure out this total column, I'm multiplying across. So 0.4 times 50 is 20. 1 times X is X. And this last column would be 0.6 times X plus 50. It's the sum of these equals the mixture. Guys, no matter how confident you feel in decimals, please just check them in your calculator because some of you guys do decimals wrong. When I distribute, this is negative 6x plus, okay, just to model for you, 50 times 0.6 is 30. Again, no matter how confident you are, please use your calculator to help you. I'm going to subtract 0.6x. So again, I know some of you feel confident, but please just check it. 1 minus 0.6 is 0.4. So I have 0.4x equals 10. I'm going to take 10, divide it by 0.4, x equals 25. Your biggest mistakes in this problem are the decimals. Just being almost overconfident in your decimal ability and making a coefficient incorrect. So that's a bummer, right? Especially if you have a calculator, check yourself. So please use the calculator to ensure your correctness. All right, the last one, I'll just start it with the table. I don't think I'll finish it just because this video is getting kind of long. You have a solution containing 10% acid and 30% acid. So let me just set up this table real quick. You must add 1 liter of the 10% solution to, or how much of the 30% solution must you add to 1 liter of the 10% solution to create a mixture that is 22%. Okay, so I had 1 liter of 10%. I'm adding an unknown amount of 30% to get a mixture that's 22%. Filling in these percents. This would be x plus 1. I had 1 liter, I added x. 1 times 0.1 is 0.1. This is 0.3x. This is 0.22 times x plus 1. Oh, geez. Alright, so the sum of these would equal this, and then you'd solve. Whew. That was a tough one. That was a really long video. He doesn't care.